Hello, and welcome to another Algebra 2 lesson. This is lesson 7.4, our objective, add or subtract rational expressions. Adding or subtracting with like denominators. Let A, B, and C be expressions with C not equal to 0. Addition. A over C plus B over C equals A plus B over C. Just like if we were adding 1/5 plus 2/5. To be able to add fractions, we need a common denominator. The denominators have to be the same, and when we add them, it stays the same. 1/5 plus 2/5 is 3/5. Same thing works with subtraction. If the denominators are the same, when you add or subtract, that denominator will stay the same. And then you do the subtraction with the numerators, a minus b, or in this case, 1 minus 2, being -1/5. Now, let's try it with algebra. 7 over 4x plus 3 over 4x. The denominators are the same, so add the numerators. Keep the denominator the same. 7 plus 3 is 10. 10 over 4x. Well, this would be the answer, except we can simplify. What number divides evenly into 10 and 4? That's right, you can divide them both by 2. So you divide those by 2 and you get 5 over 2x. Example 1b, 2x over x plus 6 minus 5 over x plus 6. Notice the denominators are the same. So keep the denominators the same and do the subtraction with the numerators. 2x minus 5. Well, those are not like terms. You can't subtract them. You just write it out, 2x minus 5 over x plus 6. And that's your final answer. And there's example 1. So the algebra, just like the numbers, you have to have the same denominator. They have to be the same, and then when you add them, it stays the same. If you think about pizzas, if you had a small pizza and you cut it into 5 pieces, and you had 1/5 of one pizza left and 2/5 of another, and you put them together in the same box, you would have 3/5. So the fifths tell you what size the pieces are. So that has to be the same and stays the same when you add those numerators. Works the same with subtraction. So keep that denominator the same when adding or subtracting. Okay, adding or subtracting with unlike denominators. The first thing you have to do is create a common denominator. A over c plus b over d. Well, our common denominator is going to be c times d. So we multiply the first fraction by d over d. Multiply the second fraction by c over c, so that they both now have the same denominator, and we get AD plus BC over CD. Also works with subtraction. Now, ideally you want to find the lowest common denominator, but you can always find a common denominator of 2 rational expressions by multiplying the denominators. However, when you use the lowest common multiple of the denominators, also known as the lowest common denominator, it is less work to simplify the answer. Let's see what I mean by that. If we are adding these 2 fractions, first thing we have to do is get a common denominator. One way to get a common denominator is to multiply the 2 denominators together. So 7 times 3 is 21. So to add these together so that they have a common denominator, we would first want to multiply this first fraction by 3 over 3 and multiply the second fraction by 7 over 7. So multiplying by 3 will create the 21, but we're only allowed to multiply by some form of the number 1. Because 3 divided by 3 is 1. So we're not changing the value, we're just changing the appearance. So multiply Now here we had to multiply 3 by 7 to turn it into a 21. So multiply the top by 7 because then we're really multiplying by 7 over 7, which equals 1. Changing the appearance, but not the value. And then add your numerators, 9 plus 14. Final answer, 23 over 21. All right, number 2. We could do 10 times 5 is 50 and use that as our common denominator. But if we do that, our numbers get bigger. So there's an easier way. But I'm going to go ahead and do this first, because that's what it said on the previous page. It says you could always find a common denominator of two rational expressions by multiplying the denominators. So if I multiply 10 times 5, I get 50. So this is 35 over 50. This is 80 over 50. So we get 115 over 50. But then we have to simplify. We can divide these both by 5. And we get 23 over 10 for our final answer. Well, we didn't have to do it that way. We didn't have to use 50 as a common denominator. What's a smaller common denominator we could have used for 10 and 5? Well, we can turn a 5 into a 10 by multiplying it by 2. So sometimes you can turn the smaller number into the bigger number. So this would now be 7 tenths plus 16 tenths. And then when you add those, you get 23 over 10. Same answer, different way. So we have to be able to do all of this with algebraic expressions in our fractions. You can always get a common denominator by multiplying the two together, but sometimes there's a smaller one. Find the sum, adding with unlike denominators. The first thing we're going to want to do is rewrite these in factored form, at least the denominators. (3x squared plus 3x) has a GCF of 3x that we can factor out, and we get x plus 1. Double check if I multiply this back. Does it equal what I started with? It does. Okay, so there's a factored form. Let's figure out our lowest common denominator. If you start with one of the denominators and then combine it with any other factors that you see. A 3x we can turn into a 9x squared because we can multiply that by 3 and another x and create a 9x squared. But we also have this factor of x plus 1. So we have to include all of the factors that we see. For example, if we go back to this 10 and 5 example, if we put these in factored form, 10 is 2 times 5, and then this is just a 5. So the lowest common denominator would be the 2 and the 5, but we don't have to multiply by another 5 because a 5 is already represented. So if we did 2 times 5 times 5, we got the 50, which was more work. And if we just do this, we don't have as much simplifying to do at the end. So don't include any of those factors twice. So just x plus 1 and a 9x squared. We're going to turn both of these into that common denominator. So we're going to multiply by, look at where we're trying to get to, 9x squared times x plus 1. It already has a 9x squared, so it needs to be multiplied by x plus 1. Whatever we do to the denominator, we also have to do in the numerator. Then for our second fraction, to create that 9x squared times x plus 1, what are we going to multiply by? It already has the x plus 1. We need to turn the 3x into a 9x squared. So we're going to multiply top and bottom by 3x. Okay, that'll create 7 times x plus 1 for the first numerator, plus 3x times x, 3x squared, over our common denominator. And now that we have a common denominator, we can add these together. You could have multiplied this at that stage, 7 times x plus 1. Just make sure you do it eventually. We get 7x plus 7 plus 3x squared all over our common denominator. All right, this could be the final answer, but we don't want it in that order. So we're going to reorganize our numerators so that the biggest exponents are first, descending order by exponents. And it's okay to leave the denominator in factored form. It's actually preferred. And this is our answer. All right, these take practice. The more of these you see, the easier it will become. Number 4, subtracting with unlike denominators. All right, factor our denominators. Double bubble. Find two numbers that multiply to be 3 but add to be -4. Okay, double check. -3 times -1 is multiply to be 3 and add to be -4. Okay, so we factored our denominators. Now decide what is your lowest common denominator, which is the least common multiple of all of your denominators. Let's start with the first denominator. We have a 2 and an x minus 1. We have to include all the factors so that we can create this common denominator from both of these. So we have an x minus 1 already. We need an x minus 3. All right, we can create this denominator by multiplying this first one by x minus 3 over x minus 3. And what are we going to multiply the second one by? That needs a 2. So we're just going to multiply this by 2 over 2. Be careful with this. Don't just distribute that 2. You have to multiply x plus 2 times x minus 3. So multiplying that. Okay, there's the first fraction, minus 2 times -2x, 2 times -1, all over our denominator. Okay, this one's pretty tricky because of the subtraction. We've got our common denominator, so we want to subtract these, but it's minus this stuff. So that's really got to be change. We have to change the signs. Change subtraction to add the opposite. Let's combine like terms here. I'm going to go left to right through this numerator, but don't forget we have to change some signs. Minus 3x plus 2x. Minus a negative 4x would be a plus 4x. And minus a negative 2 becomes plus 2. All over our common denominator. Combine like terms. Denominator staying the same. And sometimes this would be the step where we would be done. But this time we're not. We have to keep going and simplify. The numerator can factor. Now that we combined like terms and we made it all one big fraction, we're going to factor this, double, and see if anything will cancel out with the stuff in the denominator. So two numbers that multiply to be negative 4, but add to be positive 3. Multiply to be negative 4, so 4 and 1. Multiply to be negative, so we need one negative, one positive, but they have to add to be positive. So x plus 4 times x minus 1. Ooh, what do you notice? These two factors are the same. Anything divided by itself is 1. So those cancel out. And write down what's left. And there's our answer. Now, for what x is not allowed to equal, anything that disappeared in the process that would have made the original denominator 0, we have to mention at the end. X cannot be 1. The x minus 3 part is still in there, so we don't have to worry about that. Just the things that disappeared along the way. All right, that's example 4. Example 5. We want to use the skills we were just working on. Adding fractions together, getting common denominators, simplifying fractions, and apply that to example 5. In a previous section, we did 3x plus 5, and we divided by x plus 1, and figured out that we could get a whole number, and then our remainder became the fraction. Well, there's another way to do this. We can create it into 2 separate pieces with an addition, to where one of them, the denominator is going to cancel out. So if we want an x plus 1 to cancel out, that means we need to be able to factor out this 3 so that it can be an x. In order to do that, to factor out an x plus 1, we need a 3x plus 3. But it's not supposed to be plus 3, it's supposed to be plus 5. So we're going to write it as 2 separate pieces, the 3x plus 3 separate from the plus 2. So let's break this up. It's kind of like we're doing the other stuff backwards. We're breaking it into the pieces that we want. So 3x plus 3 over x plus 1 plus 2 over x plus 1 is equal to this original. And now we can factor out this x plus 1. Now that we factor out that 3, these x plus 1s cancel out. And we get 3 plus 2 over x plus 1. We want to write it in the same order as this g of x function. So our new g of x, fraction first, equals 2 over x plus 1 plus 3. All right, we got this form. Whew, that was a lot of work. Wants us to graph the function and describe the transformations. So let's talk about the transformations. That'll help us make a sketch of a graph. So our h, x minus h is -1. That means that's a horizontal shift left 1. And then our k tells us the vertical shift, k is 3. So that's up 3. So as we make a graph, our asymptote would go through the x-axis at -1 and through the y-axis at 3. Remember, these with the x's and the denominators give you hyperbolas that approach the asymptotes, and it's 2 separate branches. To get a really good graph, we would have to find some exact points, and we'd use a grid paper, graph paper, or graph it on the computer. Okay, and it said to compare it to a over x, so they didn't want us to say the vertical stretch by 2. This is a vertical stretch by 2 if we're comparing it to 1 over x, but they said compare it to a over x. So we didn't have to account for that too. So there's our transformations, there's our graph, here's our equation. And that's example 5. Now, if you're struggling to get this part, you could still divide 3x plus 5 divided by x plus 1. You could still do that. It's just not how they want you to do it. Where you divide this first term by this first term, 3x divided by x is 3. Multiply. Subtract, change the sign and circle it, change the sign and circle it. 5 minus 3 is 2. So we get 3 plus the remainder over the divisor. And notice now I get that 2 over x plus 1 plus 3. We rearrange the order. So that was the way we did it in a previous section. But this one, they really want you to break it apart and get your 2 pieces so that you have something that you can factor and cancel out that denominator and see the 3 shows up this way. And then there's your other fraction. All right, 2 different ways to do example number 5. Might be a good place to pause if you're watching the video, try some problems, and then come back when you're ready for complex fractions. Simplifying complex fractions. Those are fractions inside of fractions like this, except for it's going to be with algebra stuff. There are 2 different methods. I'm going to do this one problem with each of the methods so you can see that they both yield the same answer. Method 1, if necessary, simplify the numerator and denominator by writing each as a single fraction. Then divide by multiplying the numerator by the reciprocal of the denominator. Okay, let's read that again. If necessary, simplify the numerator and denominator by writing each as a single fraction. Okay, so this numerator, we want that to be one fraction. The denominator is already one fraction, but we want to do this part. So get a single fraction for the numerator and denominator. Then divide by multiplying the numerator by the reciprocal. So instead of dividing, we're going to multiply by the reciprocal. We're going to flip over the bottom fraction. Okay, first things first. Method 1. Let's get that top 2 fractions into one fraction. So what's a common denominator with 3 and 2? 6. So to turn this into a 6, we have to multiply by 2 over 2. To turn this into a 6, we're going to multiply by 3 over 3. Multiply, multiply, now we can subtract. All right, we've accomplished the first part of method 1. Write each as a single fraction. The numerator and denominator each as a single fraction. So we have one fraction divided by another fraction. Then divide by multiplying the numerator by the reciprocal of the denominator. So this guy's going to get flipped over. So 1/6, instead of having 1/6 divided by 3/5, we're going to do 1/6 times its reciprocal, 5/3. And multiply your fractions, write down your answer. And there it is, 5/18. Well, that's method 1. Now let's try method 2. Multiply the numerator and denominator by the LCD of every fraction in the numerator and denominator, and simplify. Multiply the numerator and denominator, so everything, basically, by the LCD. Okay, let's copy down our original problem. And multiply by the LCD, lowest common denominator of 2, 3, and 5. So you need a number that is a multiple of 2, 3, and 5. Multiples of 5 are 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and so on. So which one of those is also a multiple of 2 and 3? 30 is the number we want. So we're going to multiply the numerator by 30 and the denominator by 30. Any number over itself is 1. I'm going to make these look like fractions. Since we have fractions and fractions, I'm going to write it as 30 over 1 divided by 30 over 1. And that's what we're multiplying by. Okay, here we go. We have subtraction, so we're going to have to distribute 30 times 2, 1 times 3, minus 30 times 1, 1 times 2, and the denominator, 3 times 30 over 5. Notice this did not create common denominators. What it did instead is it's going to help us cancel out all of these 3 denominators. What's 60 divided by 3? 20. What's 30 divided by 2? 15. And what's 90 divided by 5? All right, so we have 20 over minus 15 divided by 18. 20 minus 15 over 18. Same answer we got when we used method 1. All right, let's look back at this, because this step here, you hopefully can skip it once you get the hang of this. Because look, if we do 30 times 2/3, well, 30 divides evenly by 3. That's why we are using 30. So 30 divided by 3 is 10. 10 times 2 is 20. Can jump right to here. 30 times 1/2. Well, what's 1/2 of 30? 15. And here, 30 divided by 5 is 6. 6 times 3 is 18. So hopefully you can jump right over this step and go to here, because this number is designed to cancel out all those denominators. So 30 divided by 3 was 10, multiplied by the top. 30 divided by 2 is 15, multiplied by the top. 30 divided by 5 was 6, multiplied by that top. And there's your answer. Okay, method 1, method 2, that's how it works with numbers. Now let's do it with algebraic expressions. Simplifying a complex fraction. I am going to use method 2. I want to cancel out these denominators as quickly as I can so that I don't have fractions inside of fractions anymore. We want it to not be a complex fraction. So look at our denominators. We have x plus 4, and an x. So we don't have to write x plus 4 twice. We just need it once. But then we have this x, which is different than these factors. So we need that also. And that's what we're going to multiply the numerator and denominator by. Put it over 1 if you want to. So when we multiply this here, we get 5. I'm going to go ahead and put the x there. 5x times x plus 4 over x plus 4. Notice these x plus 4s are going to cancel. If you want to cancel them right away and not even write them down, you can do that and just write a 5x. But then when I'm doing this denominator, because of the plus sign, I have to multiply it by each fraction on either side of the plus sign. So x plus 4 times x times 1 over x plus 4. So if you're already simplifying in your head and canceled out those x plus 4s, you'd only write an x. Plus 2 over x times this. Okay, if you didn't do the canceling in your head, you're doing it now with me. Those divide to be 1, sorry. Anything divided by itself is 1. This x plus 4 cancels out this x plus 4, and this x cancels that x. So all of those 3 denominators got canceled out. Let's write down what's left. 5x on the top. The denominator is x plus 2 times x plus 4. Okay, this is not completely factored because of this plus, so we're going to have to distribute, combine like terms. Two x plus x is 3x. And there's our answer. Now, what is x not allowed to be? Well, the way your textbook does this Big Ideas Math, they don't worry about this being 0. What they worry about is what changed from the beginning to the end, and that is that back in the beginning, x plus 4 couldn't be 0 and x couldn't be 0. So x can't be 0, and if x plus 4 can't be 0, then x can't be, what would make that a 0? Negative 4. So those are the two things we have to write down that x is not allowed to be. And that's example 6. To add or subtract rational expressions, what must we have? We have to have common denominators. Doesn't matter if they're numbers or rational expressions, but common denominators are needed. And that leads us to Big Ideas Assignment 7.4. Hope you had a happy Valentine's Day, which is our state's birthday. It was Arizona's birthday on February 14th. All right, and there's more examples on the following pages. I will make a second video separate from this one if you want to go and watch those additional examples. Remember, when you are adding things that already have a common denominator, you just have to do the math with the numerators, but make sure your answer is in simplest form. All right, thanks for watching. Have a great day. Watch video 2 if you want to see more examples.